I would like also to thank the organizers for the invitation. So today I'm going to talk about the synthesis of substituted azepane by ring expansion. But at first, oops, I cannot, I cannot put this second slide. I don't know. Can you do it for me?
Just click the right arrow in the screen.
Oh, okay. Okay, great. Thank you. So at first, what is our portfolio? Well, we are in multidisciplinary project with physical chemists, biologists and physicists in order to do the vectorization of drugs toward the tumor in order to decrease the secondary effect. But before doing the vectorization, the thing that we have to do is to synthesize the compounds. And we are synthesizing natural products with bioactive, biologically active activity or complex molecules, so which are bioactive. But in general, whatever you are doing for the synthesis of this complex molecule, you are always, you are always running into synthetic problems. So in order to solve this kind of problems, we develop synthetic methods, and we are mainly in enantioselective reaction, rearrangement, enzymatic reaction, and mainly in organometallics. And now we are using plasma gas in order to do organic synthesis. So in general, the thing that is happening is these compounds as in general antifungal, anti-inflammatory or anti-tumoral activity. So we were interested in the synthesis of this complex molecule. We have seen with Dr. Vidal this afternoon that we were doing the synthesis of a monster, and here it is still a monster. So this product is called emikelide, is very cytotoxic. The EC50 is around 1 to 0.1 nanomolar, and it has an original mode of action. This product has the carbon skeleton with 46 carbons, and we have 21 stereogenic centers to control, and 2 lactones, which are represented in here. And in fact, we completed the synthesis recently, and we published this synthesis in 2019. So, I mean, this compound has this kind of lactone, oxygenated heterocycle. For example, we were interested in the synthesis of this lactone in here. But if we were interested in the synthesis of this heterocycle, we were also interested in the synthesis of nitrogen-containing heterocycle. And in fact, if you are looking at the most present cycle in drugs on the market in 1914, but still now it is the same classification. The first substituent that you can meet in drugs is the benzene ring. Then you have the pyridine, then you have the piperidine, which is third, the piperazine, which is fourth, and then after you have the imidazole, you have the spironolidine in the 8th position, and the azepane, which are at the 58th position. But this kind of structure are also present in natural products and bioactive compounds. If they are in the 15th, 8th position, it's maybe they are not so easy to synthesize when they are substituted. So you can, for example, find this kind of heterocycle in balanol, which is an inhibitor of kinase. You have also this product, which is a natural product, neostenine, which is an antitussive. You have this product in here, which is an anti-affective, or azelelastine, which is an antihistaminic compound. And all these compounds has this azepane ring at this position. So how can we synthesize this azepane? Well, we have envisaged to synthesize this azepane by a ring expansion. If you want to have a 7-membered ring, the thing that you can do is to start from a bicyclic compound, which has a 6-membered ring and a cyclopropane or aziridine at this position. And if you are able to cleave this CN bond, you will have the ring expansion to lead to the formation of the azepane. You can start from another bicyclic compound with a 5-membered ring and a 4-membered ring, or you can start from a 4 and a 5-membered ring. And for our part, we have envisaged to synthesize this azepane from this bicyclic 6+1 or 5+4 4. So at first, let's have a look at the synthesis of this kind of the formation of azepane from this bicyclic compound, the 6+1. How can we do it? Well, if we are treating this kind of structure by a nucleophile, you have two possibilities. Either the nucleophile can attack on this carbon and you will have the cleavage of the CN bond at this position to lead to the formation of the 7-membered ring, or the nucleophile can attack at this position and you will have the cleavage of the CN bond and you will have the formation of the 6-membered ring. So we have a problem of regioselectivity. How can we do in order to have only the attack of the nucleophile on this position to have the formation of the 7-membered ring? Well, if you look in the literature, the thing that you can find, and we were involved in this kind of a reaction, if you have an aziridine with a trifluoro group, methylene trifluoro group at this position, if you are treating this compound by an acid in the presence of water, you have only the attack on this position, not on this one. So the trifluoro group in here can protect this carbon at this position. The other possibility is also to have another electron withdrawing group, which is an ester group. And here also, if you are treating this 3-membered ring by an acid, you can get the formation of the ring opening and the acetate is at this position. You do not have the attack on this carbon at this position. So in order to have the formation of this 7-membered ring, azepanone, for example, you can start from this bicyclic compound. But here you need to have an electron withdrawing group, either an ester or a methyl trifluoro group at this position. So at first, have a look how we can synthesize this kind of bicyclic structure. We have envisaged to synthesize this kind of bicyclic compound from this unsaturated bicyclic product. The hypothesis was maybe that we can get access to the formation of this bicyclic compound from a ring metathesis reaction applied on this diene. And this diene should be coming from this aziridine that we can treat by this acyl chloride in here in order to get the formation of this unsaturated compound. And this product should be obtained from this aziridine by an allylation. So at first, we tried to synthesize this kind of azirine. So we started from this ketoester, treated this ketoester by this hydroxyamine in methanol and the sodium acetate. We get the formation of the corresponding imine. And then if you are treating this compound by tesyl chloride in the presence of triethylamine, under basic condition, you have the formation of this tosylate, formation of the anion, and then you have the attack on the anion onto the amine, and the tosyl is it's a good leaving group, so you can get the formation of this azirine. Now, we have also to synthesize this trifluoro compound in here, this azirine, with a trifluoro group at this position. For doing this, we took this acetylenic derivative in the presence of the Tony reagent and TMS azide in the presence of copper acetate and sodium acetate, 1.5 equivalents. Under this condition, we got the formation of the substituted azirine. How can we explain this kind of transformation? Well, if you treat an acetylenic in the presence of this Tony reagent and the copper acetate, you have the formation of a radical. The radical can attack this acetylenic. You will have the formation of this vinyl radical, and then you will have an oxidation due to the formation of this intermediate, copper intermediate. So you will have the formation of the carbocation, regeneration of the catalyst, and then this anion can be attacked by this TMS azide, as you have the acetate in the reaction media. So you will have the formation of this N3 minus that will lead to the formation of this vinyl azide. If you are eating this intermediate at 80 degrees, you will have the evolution of nitrogen, formation of this nitrane that can be attacked by the double bond in order to get the formation of this azirine. So we have two azerine with electron withdrawing group, the CF3 group and the S2 group. So now we have to transform this compound into this bicyclic product via this diene. So at first, we have treated this azerine in the presence of this allyl bromide and indium. We got the formation of the allylic product, azeridine, and then by treatment with this acyl chloride, you get the formation of the metathesis reaction, formation of the double bond. Now we did the hydrogenation and we obtained the formation of this kind of bicyclic compound, which is saturated. The reaction is very general. You can have, for example, at this position, a phenyl with a bromide in the ortho position. You can have a bromide or methoxy in the meta position, a trifluoro group in the para position. Here you can have a pyridine with a chloride. You need the chloride, otherwise the nitrogen is too basic in here and the reaction is not working. Now you can have also alkyl group at this position, such as a methyl, a propyl. You can have this side chain with a phenyl, and you can have also a different aromatic here when you have a trifluoro group at this position. And you can see that the yields are not too bad, except maybe this one with the bromide in the meta position, but in general, the yields are not too bad. I have to say that all the yields in here were over the 4 steps. So, I mean, it's the overall yields are not too bad. So now, having this compound in hand, we try to transform this compound to the azetidine, the 7-mandatory. So for doing this, we try to find the best conditions. And the best conditions were the following. If you are treating this bicyclic compound in here by acetic acid in the presence of BF3 in methylene chloride at 0 degrees for 1 hour, you get the formation of the ring expansion with an ester group at this position. The reaction is very general. You can have also a different group at this position. So you have, for example, a phenyl with an electron withdrawing group that says a CF3 group. You can have a bromide, a methoxy in the meta position. You can have also, in this condition in here, if you have a bromide at this position in the ortho position, it is not, it's not working. What is this? It's not working. Even if you have, for example, also a nitrogen in here, the yield, you cannot have the formation of the ring expansion, probably due to the steric hindrance at this position, and also to the nitrogen that can quench this kind of reagent at this position. You can have also alkyl group at this position, methyl, propyl, and a side chain with a phenyl group. As you can see also, the diastereoselectivity in between this ester group in here with the ester group are pretty good. The diastereoselectivity is around 95 to 5 or 90 to 10. So the yield are good and the diastereoselectivity are really good too. So you can have also the variation of the acid. You can have, as I said previously, an ester group with a methyl and methyl. You can have a side chain with an unsaturation. You can have also a piperidine and here with a chloride. You need to have the protection of this nitrogen by the chloride, otherwise it's not working. You can have also a thiophane or a furane, or you can have also an unsaturated ester. Here also, the yields are not too bad. They are around 99% to 70%, except for this one, where the yield is really average 38%. And also in here, the diastereoselectivity is excellent, 95 to 5. Now, you can have also a diversity of nucleophile. You can have also this kind of thioacid in here. And if you are treating the same compound in here with an ester group at this position, the thing that you obtain is the formation of the corresponding ring expansion with a yield of 71% and a good diastereoselectivity. So we were able to obtain the formation of this acetidinone, azepane, for example, with an ester group in here, a quaternary center at this position coming from this bicyclic compound. So it is very nice to have an ester group, but maybe it's much better to have a trifluoro group. Why? Well, if you are introducing, for example, a trifluoro group in molecule, it can be advantageous because you can have the biological activity of the compound that can be increased. So, for example, if you are introducing fluorine in a molecule, you are increasing the metabolic stability. And this compound is, for example, with the fluorine, 50 more times efficient than the non-fluorinated analog. You can also increase the lipophilicity of the compound, and you are increase of the membrane permeability. You have also an influence on the molecular conformation. For example, this trans conformation is favored compared to the cis and the gauche conformation. And this can be important about the reactivity with the protein, the active protein. You can have also the modification of the pKa. For example, for an amine without any fluorine, you have a pKa of 10.7. With a fluorine, it decreased to 9. With 2 fluorine, it decreased to 7.3. And if you have 3, you go to a pKa of 5.7. So it will be much better to have this kind of azepane with a trifluoro group at this position than an ester. How can we do it? Well, maybe, I'm sorry, as you can see, if you are introducing, for example, a trifluoro group on a piperidine from this compound, which is an antagonist of the GnRH, which is used in the regulation of steroid hormones, you can increase the bioavailability of the compound. The EC50 are practically the same, but if you are looking at the bioavailability, it's much better for this compound with a trifluoro group than without this trifluoro group. That means the compound is going to be a little bit more active if you have this kind of trifluoro group in the molecule. So now, how can we synthesize this compound? Well, maybe we can start from this trifluoro bicyclic compound in order to see if we can get the formation of this azepanone. So how can we do it? Well, by treatment of this compound by acetic acid in the presence of BF3 etherate. And we obtain the formation of the desired product. The reaction is general. For example, you can introduce an acetyl groups at this position. You can have, for example, a phenyl. You can have a phenyl with a bromide in the para position. Oops, sorry. In the para position, or you can have a methoxy. And here also, the diastereo selectivity are not too bad, and the yield are in between 80 to 70%. Now, how can we explain the formation of this compound? Well, you have an acid, and you have also a Lewis acid, BF3 etherate. The thing that we are supposing that is happening is that probably you have the complexation of the nitrogen by BF3. So after, if you have the formation of this intermediate, you can have the cleavage of the C end bond in here that will lead to the formation of the carbocation. And then the nucleophile will attack on this position in order to get the formation of this azepanone, which is substituted in here by a quaternary center. Of course, you cannot exclude that you have the complexation of this carbonyl by the BF3 at this position. So, of course, we can, from the azepanone, we can have the formation of the azepane. If you are treating this product by LH, you get the formation of the reduction of the amide and also of the ester. So you have the formation of this hydroxy group at this position. If you have the ester, if you are treating this azepanone by LH, you get the reduction of the ketone, the ester, and the second ester to get the formation of this diol at this position. Now, if you want only to have the reduction of the amide, You treat this compound by BF3 dimethyl sulfide, and you get the formation of this azepane with an ester group in here and a second ester at this position. And here also, for all this compound, the diastereoselectivity is good, 90-10 to 95-5. So, I mean, we were able to obtain the formation of this azepane or azepanone with a trifluoro group at this position, a quaternary center at this position that is coming from this bicyclic compound. Now, if you want, as I have to point out that all the compounds that we have synthesized are racemic. Now, if you want to have this azepane with a trifluoro group at this position and a substituent at this position in a chiral, optically, I will say optically active, what do you have to do? Or what is our hypothesis? Well, we have envisaged to synthesize this trifluoroazepane from this bicyclic compound, having a 5-membered ring and a 4-membered ring with a trifluoro group at this position. What is our hypothesis? Well, maybe we can have access to the formation of this azepane, where you have a nucleophile in here and a trifluoro group at this position, by also a ring expansion applied on this kind of pyrrolidine, having a trifluoro group at this position and a good leaving group on this carbon. And the hypothesis was that if we have a nitrogen which is nucleophilic enough, you will have the attack on this carbon. As you have a leaving group, you will have the formation of this kind of bicyclic compound in here. And then, if you have a nucleophile, probably we will have the attack at this position, as in the case of the aziridine, the trifluoro group will not allow the attack of the nucleophile at this position. If we have the nucleophile that attack at this position, we will have the cleavage of this bond, C-N bond, and we will have the formation of the 7-membered ring. This compound should be obtained from this amino ester that were coming from the proline by an homologation. So at first, we tried to transform L-proline to the corresponding compound, which is represented in here. So at first, we treated this compound by oxalyl chloride and this TMS diazomethane. We got the formation of this diazoketone. And then if you are treating this diazoketone by silver salt, you get probably the formation of a Wolff rearrangement that lead to the formation of this ketane. And if you add the methanol in the reaction media, you get the formation of the corresponding ester. The transformation is pretty good, 90%, and we had a very good enantiomeric excess, 99%, if this one is 99%. So you have a good transfer of chirality. Now, having this compound in hand, we try to transform this product to the corresponding alcohol. So at first, we treated this compound by TMS CF3 in the presence of TBAF, and we obtained the formation probably of this ketone intermediate. After reduction with sodium borohydride, we obtained two diastereoisomers that we could separate the syn, the syn and the anti in a ratio 40:60. Now, having this compound in hand, the thing that we have to do is to transform this carbamate in here to the corresponding benzyl group in here, because we need to have this nitrogen nucleophilic enough in order to do the attack on this stereogenic center in here if it's activated at this position. So for doing this, we had to do a hydrogenation treatment with benzyl bromide, and we got the formation of the corresponding benzylic derivative for the syn and for the anti. The yield, as you can see, are not too bad, 66 to 82%. So now, having this product in hand, we try to do the transformation, the ring expansion of this 5-membered ring to the formation of the 7-membered ring. And the best conditions that we found were the following. If you treat this alcohol by tryptic anhydride in the presence of this proton sponge, which is represented in here, at 40 degrees in methylene chloride, in the presence of a nucleophile, you get the formation of the 7-membered ring, where these two groups are in a cis position via this aziridinium intermediate. The reaction is very general. You can use, for example, alkylate, such as a benzoate, an acylate, and you can get the formation of the corresponding ether at this position. You can use acetate, but you have to use the tetrabutyl ammonium acetate in order to have a good yield in this kind of compound in here. You can use a thiophenol, and you have the formation of the corresponding sulfur derivative. You can use different amines, such as, for example, the benzylamine, allylamine, morpholine, or the proline ester. And you can see here also that you have the compounds that were obtained with good yield, but also with a good diastereoselectivity and also enantioselectivity. For example, we were also able to introduce a derivative from the hydrazine, and the yield is pretty good, and an azide also, but you have to use the tetrabutyl ammonium azide, or you can have also a sodium amide, and you have the amide at this position. Here the yield is 60%, and the enantiomeric excess is 99% if this one is 99%. So you have a really good transfer of chirality. And we were sure about the structure of this compound because we have the X-ray diffraction of this product in here. So you can also have the formation of CC bond, as you can have the dimethyl malonate in here. The yield is around 64%. You can also treat this kind of acetidinium in here by a cuprate, and the yield is around 52%. With a cyano, you can introduce a cyano, and here also the yield is good, and the enantiomeric excess is excellent. So now we try to also to do the ring expansion of the other diastereoisomer, which is represented in here, the anti-diastereoisomer. Under the same condition as previously, if you are treating this compound by triflic anhydride in the presence of proton sponge, methylene chloride 40 degrees, you get in the presence of the nucleophile the formation of the ring expansion where the nucleophile and the CF3 are in a transposition. Here also, the diastereoselectivity is excellent, and the reaction, the ring expansion, is done via this kind of intermediate. The reaction is also very general. You can introduce acylate, benzoate, for example, in here. And the yield is pretty good, and the enantiomeric excess is excellent. An acetate, you can have also the sodium amide also, and you have the formation of this amide at this position. You can have also the aniline. Normally, aniline is not too nucleophile, but you can see that the yield is good even with an aniline. You can have an allylamine, or you can have diallylamine, or you can have a cyano group in here. And you can see that the enantiomeric excess is good, and also the diastereoselectivity. You can have also a scope that can be expanded. If you are taking, for example, this piperidine with a methoxy group in here, you can have the formation of this azepane which are tri-substituted. And here also, the diastereoselectivity is good. You can use different nucleophiles, such as the diallylamine, or you can have also an ester group at this position, or a cyano group in this position. And each time, we have good yield and good enantiomeric excess for all the azepane. So as we knew that this reaction was working, we tried to apply this reaction to an analog of a biologically active compound. For example, azelastine, which is an antihistaminic. As I said previously, if you are introducing a trifluoro group in the alpha position of the nitrogen, you can have, or you can increase the biological activity. And we have envisaged to synthesize this trifluoromethyl azelastine, which is represented in here. You can see that you have the azepane, and you have also this kind of heterocycle at this position. So how can we synthesize this compound in here? Well, we have envisaged to synthesize this analog of azelastine from this heterocycle, and also from this bicyclic azetidinium, which were coming from this pyrrolidine, where you have the hydroxy and the trifluoro group at this position. So we tried to synthesize this compound with the methyl, because you have a methyl which is present at the nitrogen on the analog of azelastine. So we took the product that we have synthesized previously. We have treated with a carbamate in here. We have treated this compound by LH, and we got the formation of the desired pyrrolidine, which is the precursor of this 7-membered ring. The second part, which is the heterocycle, we started with this cyclic anhydride that we have treated with this carboxylic acid in the presence of sodium acetate. We got the formation of this product with a double bond, an isocyclic double bond. And then if you are treating this compound by an hydrazine in toluene, in refluxing toluene, you get the formation of the desired heterocycle, this part of the molecule. Now, we took this pyrrolidine, and we treated this pyrrolidine always under the same condition, trifluoroacetic anhydride, and in the presence of the proton sponge. We got probably the formation of this intermediate. And then if you are treating by the sodium salt of this heterocycle in DMF at room temperature, you get the formation of the desired product with a yield of 70%. So this is really a short synthesis of an analog of the azelastine. So in conclusion, the thing that I try to show you is that you can get different 7-membered rings, azepanone or azepane, which are represented in here, by a ring expansion. If you are taking this bicyclic compound in here, 6-membered ring with this aziridine, with this aziridine, but you need to have an electron grace going in here. If you are treating this compound by a nucleophile in the presence of BF3 etherate, you can get the formation of this tri-substituted azepanone, where the nucleophile and the R group in here are in a transposition. Now, to get the formation of this 1,3 substituted azepane in here, the thing that you can do is to start from this pyrrolidine, where you have this hydroxy group, which is transformed in a good living group in the presence of trifluoric anhydride, and in the presence of the nucleophile, you can get the formation of this di or tri-substituted azepane via this azetidinium intermediate. You can have also different fluorine group at this position, CF3, CF2H, and a long chain with a fluorine derivative. So the thing that I have to do now is to thank all my group, for the dedication to chemistry. And I would like particularly to thank Christophe Meyer, who is the Director of Research at the CNRS. Christophe is in here, and is really an excellent chemist. I would like also to thank Alessandro Dumas, who is in here, and is now working in a company, Sequence, and Domingo Gomez Pardo, who is in here, is Assistant Professor in the ESPCI, Sarah Rioton, who is in here, now she's in Germany, and Guillaume Masson, who is in here, who is now in Switzerland. I would like to thank the ESPCI, the CNRS, the Minister of Research for the financial support, and I would like to thank Sequence and Sanofi also for their financial support. And finally, I would like to thank you for your kind attention. Thank you so much.